Hello, in this video, we're going to cover two graph algorithms, depth first search and topological sort. First, I'm going to explain the depth first search algorithm in detail, then I'll motivate why it's useful with a cool problem, where we need to use depth first search and an algorithm called topological sort to solve this problem. If you're watching this video just to see how depth first search works or how topological sort works, I would recommend looking at the description for timestamps of the video. So let's first look at what depth first search is. Depth first search is a traversal algorithm which works on directed and undirected graphs and visits all the nodes in a depth first order. What does depth first order mean? Well, it just means that the search will traverse the nodes so that it goes deeper into the graph whenever it's possible. Let's look at an example. For this graph, let's start a traversal on 0. Let's use some coloring to help with our understanding. Let's have all unvisited vertices be white and all discovered vertices be green. Initially, just the vertex 0, which we're starting on, is discovered. Now from here, we can go deeper into the graph via two available nodes, either the 1 or the 2, which are connected to the 0. It doesn't matter which one we choose, but I'm just going to go in numerical order starting with the 1. From the 1, we can go deeper either with the 3 or the 5. Let's go with the 3. From the 3, we can see that there are no more nodes which we can go deeper. In a sense, we've hit a dead end and we're finished discovering the 3. Let's introduce another color, red, to show that the visited node is finished being discovered. So now white vertices are unvisited, green vertices are visited vertices that are currently being discovered, and red vertices are visited vertices finished being discovered. When a vertex is finished being discovered, we backtrack. So in this case, 3 is finished and we backtrack to the 1. Now from the 1, we can still visit the 5, but from the 5, there are no other vertices to visit, so we say that 5 is finished and we backtrack to the 1 again. Now 1 has no more unvisited vertices it can go deeper to, so we say it's finished being visited as well and we backtrack to the 0. Now for the 0, we're finished exploring the 1, but we can still go deeper with the unvisited 2. From the 2, we can go deeper still and discover the 4. But once we reach the 4, there are no more nodes to explore, so we have reached a dead end. We can say the 4 is finished and we backtrack to the 2. And from the 2, there are no more unvisited vertices, so we can say the 2 is finished and we backtrack to the 0. Finally, the 0 is now finished as there are no more unvisited vertices it can reach, so we mark it finished and this concludes our depth first search. Notice how the order of discovery corresponds to the depth first manner in which the vertices are visited. Okay, we just saw a relatively simple example. Let's now trace through a slightly more complex example, and let's try and build up the pseudocode as we're tracing through it. The first thing is our function definition. The algorithm takes in a graph, which we're performing the DFS on, and a source vertex to start at. The next thing is that there needs to be some way for us to keep track of which vertices are visited and unvisited. In our example, the white vertices are the vertices that are unvisited, and the green or red vertices are the ones that are visited. We can track this in our code by making a map where the keys are vertices and the values are true or false depending on whether a vertex has been visited or not. Initially, all the vertices are unvisited, so we can initialize our map, setting all the values to false. Okay, now let's take a break from our code and trace through a few steps in our DFS. Let's pretend now that DFS was called with 1 as the source vertex for this example. It should make sense then that our map looks like this, where all the vertices are mapped to false except for our initial source vertex. Now we know that we want to go as deep as possible for all the vertices directly reachable for 1. In this case, there are 3 vertices, the 0, the 2, and the 3. We can pick any of these vertices, but I'm just going to stick with the numerical order and pick the 0. As soon as the 0 is chosen, we should mark it as visited. Now we check if there are any vertices with an edge to 0 which have been unvisited. The only vertex is 1. But this is already visited, and we don't want to revisit an already visited node. This leaves us with no more vertices to explore, so 0 is now finished and we backtrack to the 1. When a vertex is finished, we don't have to change that vertex to true in our visited map because it should have already been marked as true when we first discovered it. I'm going to change the color to red because visually I think distinguishing between the two will help our understanding, but in terms of our code, there's no difference. Now that we have backtracked to the 1, we can explore the 2 or the 3. Let's go with the 2. From the 2, we can see that there are 4 edges connected, the 1, 3, 4, and 8. We can't explore the 1 because it's already visited. However, we can explore either the 3, 4, or 8. Again, any choice is fine, but I'm going to stick to numerical order and choose the 3. From the 3, we notice that there are 4 edges directly connected to it. The 1, the 2, the 4, and the 5. However, the 1 and 2 are already visited, so we're left with only 2 options, which is either the 4 or the 5. Let's choose the 4. Now from the 4, we have 2 edges, either the 2 or the 3. But notice how both these are already explored. We don't want to explore an already visited edge, so since there are no more unvisited vertices to visit from 4, we mark 4 as finished and we backtrack to the 3. Because 1, 2, and 4 are all already visited, our only node left to explore from the 3 now is the 5. From the 5, we have 2 edges, either the 3 or the 6, but the 3 is already visited, so we have to go to the 6. From the 6, there are 2 edges, the 5 or the 7. The 5 is already visited, so we visit the 7. And from the 7, the only edge is the 6, which is already visited, so there's no more edges to visit. This means we mark 7 as finished and backtrack to the 6. At the 6, there are no more unvisited nodes, so we're finished and backtrack to the 5. For the 5 again, there's no more unvisited nodes, so we're finished and we backtrack to the 3. From the 3, there are 4 edges to nodes 1, 2, 4, and 5, but at this point, all of these nodes have been visited, so we have no more vertices to explore. So once again, we mark 3 as visited and backtrack to the 2. From the 2, we have edges to 4 vertices, the 1, 3, 4, and 8. Among these, only the 8 is left as unvisited, so we're going to explore the 8. From the 8, we explore the 9. And from the 9, there are no more vertices to explore, so we mark it as finished and backtrack to the 8. From the 8, we are finished and backtrack to the 2. And now from the 2, all 4 edges of 1, 3, 4, and 8 are visited, so we are finished with the 2. And we backtrack to the 1. There are no more unvisited vertices to explore from the 1, so we are finished with the 1, which was our original source node, so we're done with the entire depth first search. Now let's go back to our code and figure out how we're going to implement this mechanism. Here's what we had so far. The next thing we're going to add is a helper function, which takes in the graph G, the vertex we're currently performing the DFS on, which is U, and the visited map. We're going to be calling the helper function recursively later, so keep this in mind. We're going to call this helper function from our original DFS function, passing in the source as U initially. The first thing we're going to do in our helper function is to mark the U vertex as visited. This step should be familiar because earlier when we were tracing the code, every time we chose a new node to explore, we marked it as visited. Now here comes the tricky part. Let's assume that our graph represents an adjacency list, where each vertex in the adjacency list represents an edge connection from U to that vertex. We need to iterate through each of the vertices in the adjacency list, and if that vertex has not been visited, we recursively call DFS helper on the unvisited vertex connection to U. So let's say we had this example where U has 2 neighbors, A and B. We would recursively make a call to A because it's unvisited, but not to B because it is visited. But here's the more confusing part. If U has 2 connections to A and B, both of which are unvisited, the recursive call to A occurs first. So we would mark A as visited. But keep in mind that during a recursive call, A could discover B. So if there's an edge between the two, let's add in an edge between A and B here. We have now made it possible for A's recursive call to discover B, since there's an edge between A and B. Now since B would be discovered from A, B would have its own recursive call, and from there would be no more vertices to explore, so we would have to backtrack to the A. This backtracking mechanism can be done implicitly through our recursive stack calls, where in this case, the recursive call to B is popped off the stack frame, and we go back to the recursive call of A. And now from A, there are no more vertices, so we finish and pop off the A. And notice how from here, you can't explore B because B is now marked as visited, even though if you remember back to when the A recursive call was originally made, B was unvisited. Therefore, the tricky thing about this algorithm is that future recursive calls can affect how the current one will continue to execute. Now let's go back over the tracing of this graph again, starting with the 1 as the source. This time I'm not going to say anything and just let the animation run, but I've included a figure of the recursive stack call. Try to take some time and pause the video if you need to, in order to make sure you really understand what's going on here. Now that you hopefully understand the tracing of DFS through that graph, I want to introduce the following case. Let's pretend we run DFS with 1 as the source. It should become apparent to you that our algorithm has a problem, namely it won't reach the nodes 3 or 4. However, in the beginning of this video, we said that depth first search should reach all the nodes in the graph. Our current algorithm does fine if the graph is connected, but if there is a disconnect in the graph, the algorithm fails to reach the components which are not connected to the source. In order to solve this, we can add the following modification to our code. All this modification does is it adds a loop to our original call to DFS helper with the source. This loop checks to see if any remaining nodes have still not been visited, and if this is the case, it starts the DFS on that node. It continually does this until all the nodes are visited. This solves our case of a disconnected graph because it ensures that all nodes are visited regardless of whether they are connected to the source or not. Now that you understand the pseudocode behind DFS, let's figure out the time and space complexity. The best way to understand the time complexity is to realize the fact that each vertex can only be visited by depth first search once. Furthermore, we have to realize that although we can consider a vertex multiple times as a candidate, this occurs where we check if the visited of V is true or false. This consideration only occurs if there is an edge in the adjacency list. In an undirected graph, this edge can be checked only 2 times, from a vertex on either end of the edge. Therefore, depth first search is bounded by a constant amount of checks to edges and a constant amount of checks to vertices. So the time complexity is O of V plus E. Admittedly, I'm doing a bit of a hand-wavy job of explaining this, but a more rigorous proof of the runtime kind of goes beyond the scope of this video. Let's move on to space. The extra space we use is for our visited map and for our recursive stack calls. The visited map is bound to the amount of vertices in the graph, and in worst case, the recursive stack calls is also bound to the number of vertices in the graph. Just think of a graph where it's just a single linked list, then the recursive stack would grow all the way to the end with 1 stack call per vertex. Both of these are bound by V, so our space complexity is O of V. Before we move on, I want to just note that there are many different implementations of DFS out there. The main other one uses an actual stack instead of recursion. However, over all the different implementations, these time and space bounds are going to be the best you can get. Okay, at this point in the video, I hope you understand what the DFS does, so you might be wondering how this algorithm is useful, and I promise I'll demonstrate an application through a cool problem. But let me just talk through 2 more things that are relevant to depth first search concepts. On their own, these 2 things might not be that useful, but if you encounter graph problems that use depth first search, these 2 concepts could become quite handy in allowing you to add features to your depth first search so that you can tailor it to that specific problem. The 2 concepts are the notion of discovery and finishing time. Discovery time describes the relative order that the nodes are first visited in DFS. In our tracings earlier, we can think of this as when a white node turned green. Finishing time describes the relative order that nodes are finished. This is when a green node turned red. There are a number of ways to represent discovery and finishing time in our code. One simple way is just to append them to a global list. For discovery time, we just add the vertex to the end of the list as soon as it's discovered. This is the same place as when we mark that vertex in the visited map as true. A vertex is finished when its recursive call finishes, because when its recursive call finishes, it means that there are no more vertices it can further explore. Therefore, we can append the vertex to the end of the finishing list at the end of a recursive call. It should make sense then that for the graph we did our earlier traversal on, the discovery order and finishing order look like this. It is important to know that there can be multiple different outcomes to a depth-first search, and as a result, there can be multiple different discovery times and finishing times. The ones I've displayed here corresponds to how we were traversing the graph earlier, but keep in mind there can be other valid versions as well. Okay, now that we have finished depth-first search, let's see how it's useful through this fun problem. Let's pretend it's a weekend and you want to make the best breakfast of waffles. But in order to make the perfect waffles, you need to follow a certain order of events. For example, before we pour the syrup on our waffles, we need to heat the syrup. But since we don't want our syrup to get cold, we need to make all our waffles before heating the syrup. And also maybe we're really picky and we want the syrup to be on top of any fruit toppings that we put on our waffle. So then we need to cut and place the fruit before we place the syrup as well. Let's model this relationship with a graph where an edge from a node A to B means that we need to do the task A before we can do the task B. So for this example, there's an edge from cut fruit to place fruit because we need to cut our fruit before we put them on the waffles. There's an edge from heat syrup to pour syrup because we need to heat our syrup before pouring them on our waffles. There are a couple more edges here from cook waffle to heat syrup and place fruit to pour syrup, which should hopefully all make sense. Our entire waffle making process might look something like this. Our problem, which we're going to solve by the end of this video, is to produce an ordering of instructions where we do not violate the ordering of our recipe. So for example, one possible ordering might look like this, another possible ordering could look like this, and notice that there are multiple valid orders because there are multiple valid sequences that we can use to make our waffles. For example, once we prepare our ingredients, we can preheat our iron, but we can also make our syrup, or we can make our batter, or we can cut our fruit. One thing to know is that for valid ordering to exist, there can't be a cycle in our graph. Our graph has to be a directed acyclic graph. This is because if there's a cycle, then there's no possible way to accomplish any task without needing to have accomplished the previous links in the cycle. For example, between these three nodes, in order to do step 3, we need to do step 2, but in order to do step 2, we need to do step 1, and this is a problem because in order to do step 1, we need to have done step 3. So you can see how this problem just keeps looping us around. Even if we have other connections to this cycle, I hope you can see that it would still never be possible to come up with an ordering. More formally, this kind of ordering is known as a topological sort. A topological sort is a linear arrangement of nodes where if there exists an edge from node A to B, it means that node A comes before node B in the ordering. Less formally, this just means that all the edges are pointing in the forward direction. So for this example, notice that all the edges are in the forward direction. Therefore, it would be a valid topological sort. But let's say we try to pour our batter before we preheat our iron, then we would have a backward edge, so this would not be a valid topological ordering, and this makes sense because we don't want to pour our waffle batter on a cold iron. Okay, so how do we apply DFS to create a topological ordering? Well, it's pretty straightforward actually. We just need to make use of finishing time in DFS. We just run a DFS on the graph using any node as an arbitrary start point. We also keep a list which starts off empty but will ultimately hold our topological ordering. Then as we run our DFS, every time a vertex finishes, we just add that vertex to the front of the list. At the end of our DFS, this list will hold one of the many valid topological sorts. Here is our algorithm from DFS earlier with discovery and finishing time. We don't need discovery time, so let's get rid of that. And now let's rename our finishing time list to topo and add to the front of the list instead of the back of the list every time a vertex finishes. Again, a vertex finishes when it's finished being discovered, which occurs at the end of the recursive stack call. As a note, there are multiple different ways you can add to the front of a list in whatever programming language you use. You could just add to the top of a stack or add to the front of a linked list. It's just important that we add to the front, and this occurs in O of one time. For our pseudocode, I'm just going to say add front to get the idea across. So now let's go and trace through an example of the topological sort with the waffle graph from earlier. To start, we call our DFS with our waffle graph and some random vertex as the source. I've chosen preheat iron for this example. Now let's keep track of the graph the same way as earlier with our colors. Let's also keep track of the recursive stack as well as the current way the topo list looks. At this point, the code executes exactly like depth first search, so I'm going to be quiet and let the animation run. Pause the video if you need to in order to make sure everything makes sense. Okay, I hope that made sense. Now if we take the topological sort that the algorithm came up with, we can see that there are no backward edges. This means that if we proceed to make waffles in this order, we'll be super successful in making our waffles. And now that we have solved this waffle problem, that brings us to the end of this video. If you found it helpful, please consider liking the video and subscribing to the channel. And as always, if you have any questions, feel free to leave them in the comments and I'll do my best to answer them. Thank you for watching, and I'll see you in the next video.